Hopefully, that was a fun quiz. I hope. Oops. Fun time had by all. All right. So last time we talked about really solubility product here and KSP. And remember that KSP is basically the equilibrium constant for things that are insoluble. And they always sort of look the same way in a sense. There's always solid on the left-hand side of the arrow, always are aqueous ions on the right-hand side of the arrow. And that means in most cases, it really is just the products that you're going to have for your KSP expression. And as we saw in some examples that we did, there's a number of factors that does affect the solubility. Things like concentration of the ions that are floating around, also things like pH and common ion sounds like a good one as well. So we also talked about at the very end there that you can use the KSP to sort of your advantage to figure out something like selective precipitation. So you can figure out the concentration of a precipitating reagent that you might need to add to a solution that has ions floating around to, again, selectively precipitate off certain ions while leaving other ones still in the solution. Any questions on any of that stuff there that we talked about last time? All right, so we're gonna finish up talking about complex ion equilibrium. And complex ion equilibrium is, as the name kind of implies, an equilibrium constant for complex ions. So these complex ions are these guys where, you know, you got like a metal in the middle and maybe something like water, for example, and like maybe 6 of them with like a charge or something going on there. So a lot of times we have these metals and these guys that come on and they form a complex ion like what we see here. And we can write an equilibrium expression for it, which is the products over the reactants, just like normal. We'll take our coefficients there and take it to our exponent. This is what's known as Kf, or the formation constant, and it is the equilibrium constant for complex ion formation. As the Kf value increases, the stability of making a complex ion is increasing as well. And that's our normal sort of K reasoning there, which is if K increases, we have more products. And then on the product side, it's our complex ion. So obviously that's going to stabilize our complex ion. What we do add here are what are referred to sometimes as ligands. Ligands are Lewis bases. And if you remember, Lewis bases are things that donate. Yes, a pair of electrons. That is it. So they are the ones that donate a pair of electrons there. Like Cl minus, which are pretty good ligands because they are negatively charged, and that means they've gained electrons, so they have them to sort of donate. By the way, these ligands actually do come on one at a time. So kind of like how hydrogens are lost one at a time, these ligands are actually added one at a time. So in this particular example here, the first thing that would happen is the cobalt would pick up one chloride. And it would make something like COCl plus. And there would be a K value for that part. Then this guy would pick up another chloride. And that will make COCl2. And there would be an equilibrium for that. Then this guy would pick up the third chloride in this case, giving us COCl3 minus. And this would give, say, like our K3 if you want, K1, K2, K3. And lastly, this guy here would pick up the last chloride in the case here. And make COCl4 2 minus. And that would have a K equilibrium with it. So these are actually stepwise processes where these ligands come on. What we're looking at here is actually the overall reaction. I'll spell that right. There you go, overall reaction. And we get that by adding all these equilibrium reactions together. This cancels, that cancels, that cancels. That leaves us the cobalt that eventually will pick up 1, 2, 3, and 4 chlorides. to make our complex ion here at the end. So what we're looking at there is the overall reaction, which is what the Kf would be. By the way, I just added all four of those equations together. If I wanted the K value for it, what do I do with the Ks for each one? We do multiply, remember, we don't add those together. So here, this would be K1 times K2 times K3 times K4, right? So we do multiply them if we add them together. So sometimes in these sort of situations, you may be given the overall reaction where sort of all the ligands have already been put on there. You may be given sort of the stepwise one where you might have to add up the equations together and get an overall K value. So sometimes that happens with these sort of ligands that are being added on. Any questions on that there? Now, typically speaking, as we will see, Kf values are typically very large, usually. And that's different than what we saw as KSP, which are typically very small values. So this is sort of the other extreme. These are typically very large values of K. And that means in most cases, when you have a situation where you can form a complex ion, it is definitely favored because of the very large K value there. They're going to want to come together to make that complex ion on the other side. So some common ligands, as I mentioned, are things that really are polar and have some non-bonding electrons. So water is a really good ligand because they're on the oxygen. We got some non-bonding electrons. It's also a polar molecule, more negative on the oxygen versus the hydrogen. Again, our guys with negative is usually pretty good. Ammonia is also polar, right? It's got some non-bonding electrons there on the nitrogen as well. Something that we sometimes talk about when we deal with complex ions, which in a later chapter we'll deal a lot more with complex ions, is what is referred to as the coordination number. And the coordination number is basically the number of ligand atoms that are directly attached to the metal. So if we look at this cobalt here, basically it has, and it's actually attached to the oxygen, by the way, but I'll just write it like this. It has these 6 waters basically attached to it. And in this case, water is neutral. So the overall charge here is coming from the positive charge on the cobalt. The coordination number here is actually the oxygens that are attaching. So 1 oxygen in each of those waters are attaching. And that will give us a coordination number of 6 in this case, as opposed to, say, our cobalt there, where we basically have 1, 2, 3, and 4 guys attached there for the coordination number. Now, sometimes people think the coordination number is always this number here, and it depends on the type of ligand that you're dealing with. If you have a monodentate ligand, which is pretty much what both of these guys are, mono meaning 1, it means that basically it will attach 1 atom per molecule to the metal, basically. So that's the oxygen. In the case of water, the Cl is obviously the Cl in that particular case. But there are some ligands, as we'll see in a later chapter as well, like our friend C2O42-, a little oxalate action there. And I think I remember what it looks like. Maybe something like this, perhaps. So that's oxalate. And what happens if you have something like oxalate, for example, and a metal, it's actually going to attach 2 per oxalate molecule, which means if you had a metal with oxalate written something like this, perhaps, we would actually have, for every one of these, a coordination number of 2, and there's 2 of them, which means it would actually have a coordination number of 4, and that's what's referred to as being a bidentate, because we would have 1 more oxalate, say, on the bottom here, which would attach, and that would give us 1, 2, 3, and 4 atoms directly attached to the metal that would be in the middle, like the copper or whatever it may be there in the middle of it, or cobalt. So it's not always the number on the bottom because the ligand could actually bind in multiple places per molecule. There's actually ones that could bind, for example, in 6 places per individual molecule. So that increases, obviously, the coordination number. Any questions on that there? All right, so let's take a look at a problem here together as to how we kind of deal with these type of problems and some of the things that are a little bit different based on some of the things that we see with KFs. So in this case, we want to know, we're going to take 20 or 20 moles, no, 0.2 moles, it's like 20, of copper 2 sulfate is mixed with a liter of 1.2 molar ammonia solution. What is the concentration of the free copper 2 at equilibrium? So in this case, we're basically going to throw everything together, and our total volume here is going to be basically 1 liter, basically. So our total volume is going to be 1 liter. We're going to toss in some copper 2 that's going to come from our copper 2 sulfate. We also have some ammonia in there as well floating around. So we're going to do this table, and we're going to do this table in terms of molarity. Would be good. We're going to do it in the molarity of everybody kind of mixed together. Yeah. So since we're assuming kind of the total volume here is 1 liter, that means that initially I have 0.2 molar of the copper 2 that's coming from this guy, which is 0.2 moles divided by 1 gives me 0.2 molar. We also have ammonia here, which is 1.2 molar, as again, the total volume here is just going to stay at 1 liter. And we have none of our complex ion to begin with. Any questions so far? Now, in this case, because of the KF that we see here, and we can write the KF expression, which would be our products over our reactants. And once again, here we still need to take the 4 in this case, right? Because of the coefficient. When we look at this value of K, it is a large value or small value? It's a pretty large value. That's like to the 13, which means pretty much most everything is going to be heading in the right direction, there, right towards the products. So even though this is a reversible reaction, the first assumption that we make in these type of problems is because the K value here, their KF value is so large, we kind of assume that it's kind of a one-way street. Everybody's going to go towards the product side in this case. And what that means is the change part here is actually going to be the metal, which is the smaller number in this case. So the change here would actually be minus 0.2 minus 4 times 0.2. Why did I do 4? Yeah, it's kind of equivalent to doing like minus 4x, right? We kind of already know what x is in this case, and that's why this would be kind of like minus x, and that's what the change is going to be. Other side there, we're going to do plus 0.2. That means when we reach equilibrium, we will have none of the copper there. We will have 1.2 minus 4 times 0.2. Going to give us 0.4 molar, and we'll have 0.2 molar. Resolve any questions on the table. So in these type of problems, that's really the kind of the first assumption that we make, that pretty much all that metal, because of the K value being so large, is pretty much going to end up tied up with all the ligands. In this case, the NH3s are a ligand. Those guys are going to surround them. It's going to get all pretty much used up in this case. It's like the limiting reagent, pretty much. So what we're really looking for is what is the concentration of copper 2 at equilibrium, and that would be that guy at equilibrium, which is 0, which means that wouldn't be much of a problem if that was the answer. So that's clearly not the answer in this case, and it's really not the answer because this is still a reversible reaction, which means even though maybe we use 99.9999% of it up to make that complex ion, it is still gonna try to go back and will go back a little bit the other way. Yeah, so it's still gonna go back a little bit in the other direction. And that means that we will actually produce some copper 2 at the end of this whole process. Should that amount of copper 2 be a lot or very small? Should be very small. And that's sort of the second assumption that you make when you do these type of problems is, even though we first assume that pretty much all of it's going to be used up to make the complex ion, because it's still in equilibrium, we're going to have a little bit of it shifting back the other way. And what we should have in terms of free copper 2 in this case, or the free metal, is a very, very small amount that's still freely floating around in the solution. So typically what we do is we kind of zero it out at the beginning here. And now what we could do is actually come back and kind of call it X, because now we really want to kind of solve for what's left at equilibrium. And we could do that because based on our ice table, we now have the concentration of our product here at equilibrium. We also have the concentration of ammonia at equilibrium, and we also have the Kf value given to us. So we could actually use the Kf expression to figure out how much of that free copper 2 will still be in solution. So if we rearrange this equation, these guys are basically just going to switch places, basically. We're going to multiply the copper 2 to the left and divide the Kf back over, and you will get that the copper 2 concentration will equal the concentration of our product divided by the Kf and divided by NH3, which again, we still need to take to the 4th power. So we have all those numbers, so we'll put them in. We got 0.2. We got our Kf, which is 5 times 10 to the 13. And we have our 0.4 to the 4th. And if we do all that on our calculator here, perhaps. We end up with 1.6, hopefully, 1.6 times 10 to the minus 13 molar for the free copper 2 concentration that's floating around that solution. Is that a large number or a small number? That's an extremely small number, which essentially proves our assumption that pretty much all of it's gone, right? All of it's in that complex ion. If you really look for it hardly and go out about 13 decimal places, you will find a little bit of it floating around in that particular solution. Any questions on any part of that calculation there? So these are the two major assumptions that you want to do when you're dealing with any type of complex ion. First, we assume that the metal is pretty much going to be our limiting reagent. It's going to get completely used up. And then we need to kind of go back in a lot of cases and solve for how much is actually there. And it should end up being a really small number. So here, if you got a really large number at the end, something definitely did not go right. It changes 0.20 because a couple of things. It is because the Kf value is really large, which implies that this reaction is going to basically head towards the product side. And that means that the forward reaction will predominate. And when we look at really sort of these numbers here, the metal in pretty much all these cases will be the limiting reagent. There's less of it basically, and there's plenty of the sort of ligand present in that solution. So it will be the one that will get used up. And that's what's concentration really of our metal. And that's what we would use for our change part. So typically, because a complex ion has the metal in the middle and all those ligands attached, typically it's the metal that's like the limiting reagent in that situation. And the limiting reagent is the one that usually will get completely used up. So that's why we picked it as our change. Other questions? Okay, let's take a look at another one here. So why don't you take a couple minutes here or so and give it a try and see what you get. Here we want to calculate pretty much everybody's concentration. Based on this stepwise formation that we see here, we're going to be mixing 150 mils of the silver nitrate with 200 mils of our sodium thiosulfate. See what you cut here. So might need to combine some equations, figure out some molarity. Okay, so let's see how you're progressing. So in this case, we really kind of are looking forward to concentration of like everybody in each of these steps. So we do have a stepwise sort of formation given to us. So if we want, we can get the overall reaction here, which might help us a little bit along the way. So again, these guys are going to really cancel. That's going to leave us basically our silver plus a couple of these guys here will make our complex ion in this case. And if you wanted to as well, you could get like I got the 3 and the 2 backwards there. There you go. That's a 2, and that's the 3 up there. That's 3 and a 2. There you go. We could also get a K value for this, which would be again equal to our K1 times our K2. So if you did that, here 7.4 to the 8. Again, we're going to multiply 3.9 to the 4 here. That gives us something like maybe we'll go with 2.9 times 10 to the 13 as like our KF when we put it together. So in this case, we do want really the concentration of everybody going into this equation. So we are putting these guys together. Our silver nitrate is our source of silver. This guy right here is our source of the S2O32 minus. So that's M1 V1 equals M2 V2 action happening there. So our concentration of silver would be 150 milliliters times our 1 times 10 to the minus 3 divided by our total volume, which is 150 and 200, which would be 350 milliliters. So that those cancel. That's going to get us 150 times 1 to the minus 3 divided by 350. We got something like 4.29 times 10 to the minus 4 molar. For our S2O32 minus, we'll do the same thing. We got 200 milliliters times our 5 molar divided by our total volume of 350. That's going to get us 200 times 5 divided by 350. It's going to us 2.86 molar here for this guy. And again, our total volume coming from the 150 we mix with the 200 milliliters, giving us our 350. Any questions on how to get those concentrations? So typically when you're doing these things where you're putting them together with the complex ion, you kind of want the concentration of those ions when they're together, especially if you're going to use, obviously, here our overall reaction that's happening. Any questions on that there? So let's use that perhaps. So we're going to take our overall reaction, which again is our silver plus 2 of these guys. Going to make our complex ion here of AgS2O323 minus in this case. So at this point, initially from our calculation on the previous page, we had for silver 4.29 to the minus 4. We have 2.86 molar for this guy and 0 this guy. Once again, here we're going to use our assumption that all of the silver or the metal here should get used up. So that will be our change. Again, I do need to multiply it by 2 here for the change part because of the coefficient. Again, that's similar to 2x basically. And here we would add 4.29 times 10 to the minus 4. That means when we do reach equilibrium here, we will end up with some stuff. We will end up with 0 for our silver, which is our assumption. 2.86 minus 2 times 4.29 to the minus 4. Going to give us basically 2.86 and 4.29 times 10 to the minus 4. Of course, if any questions on that table. At this point, I just got the concentration of our complex ion at equilibrium, right? It's going to be our 4.29 times 10 to the minus 4 molar, which was one of the things we were looking for. We might not have been looking for this guy, but we also got its concentration at equilibrium as well from this table. So if we kind of look back here, we got this guy. We still need to get these 2 concentrations here. So there's a couple of ways that we could do this. You could go individually into each of those equilibrium guys that we saw. And if we look at what we have at this point, we have this guy's concentration and we have this guy's concentration, which means I actually could use the K2 expression and solve for the guy that's missing. So that's what I'm going to do because that's the information I have. I'm going to use K2 here. So I'm going to use this expression here for just the second step, and that would be our products for the second step here, divided by our reactants. And again, this is an equilibrium, which means I can write an equilibrium constant for it. So it all should work. I have all that information. Once again, these two guys are going to switch places. That's going to give me the concentration of this intermediate is going to equal this guy here. Divided by K2 and our S2O32 minus. So putting in our numbers from our table above, we will have 4.29 times 10 to the minus 4. We will have our K2 value, 3.9 times 10 to the 4. And we will have our 2.86. That's going to give us 4.29 to the minus 4 divided by 3.9 to the 4th. Divided by 2.86, going to give us for this intermediate 3.8 times 10 to the minus 9 molar. Any questions on that there? So I really just used the second step because, frankly, I have enough information to allow me to solve for this guy. Now that I solve for that sort of intermediate guy, I now have this concentration and I now have this concentration, which means I can now use the first step here to get to silver. And we use the second equation first here, and that is why there is no squaring of this guy, because I'm not using the overall equation, right? I'm just using the second step. So now if I use the first step, the K1 would be our product. Divided by our silver and our S2O32 minus. Once again, when I rearrange, these two guys are going to switch places. And that would give me that my silver would equal my K1 on the bottom. And I'll go here, S2O32 minus. So putting in our numbers, that will give us up on top will be what we just solved for, 3.8 times 10 to the minus 9, divided by our K1, which is 7.4 times 10 to the 8, and our concentration of this guy, which is again still the same at 2.86. That is going to get us 3.8 to the minus 9 divided by 7.4 to the 8 divided by 2.86. 1.8 times 10 to the minus 18 molar would be the silver concentration that is free. That concentration is large or small, which is what we would expect to be in this case. So in this case, I actually can use each of the steps as equilibriums because they are, and I can use my equilibrium concentrations and just plug and chug into there. Any questions on any of those steps there? By the way, could I have done it with the overall K value and the overall equation? The answer is yes. You could have if you wanted to, like we did in the first problem, take these guys, go into the overall expression for the overall reaction and solve for silver using the K value that we got here. And if you do that, you will hit the exact same silver concentration that we got before. So you could have, again, at the end there, solve for the silver by using the overall reaction. Minus. And our S2O2 squared. It's not gonna get it. Here we go. There you go. There you go. And we do need a squared in that case, and that would equal the KF would obviously be that value right there that you put in there. And you will get, again, the same value that we got here for this. So you could have went for the silver first and then went back to the other guy. Or you could just use each of the stepwise. The thing is, they're all equilibrium, so you could do them all. Any questions on any of that there? All right, one last one here to wrap it up together. Calculate the molar solubility of silver chloride in 1 molar of ammonia. We have a stepwise sort of process here. We have our silver chloride with our KSP, and we have our silver making a complex ion with ammonia. By the way, can I add these together? No. I'm going to say yes because I drew a line. So I'm going to say yes, I can. And when I do add these together, by the way, those cancel. And you do end up with silver chloride plus the couple of ammonias will give us our silver complex ion and our chloride. KSP, KF, are they really different? They are not. They're equilibrium constants. Doesn't matter what the little subscript is. They're all the same. So you can multiply these guys together to get the K value here by taking 1.6 times 10 to the minus 10 times our 1.5 times 10 to the 7. And it'll give us a combined K value here of 1.6 to the minus 10 times 1.5 to the 7. Going to give us actually 2.4 times 10 to the minus 3. So just because they're different K's, you can still multiply them together because they are just K values. It's the same idea as what we do when we take Ka and Kb, right? We add them together to get Kw, right? So they're all the same sort of thing, even though they have different letters. So in this case, believe it or not, it is actually just a solubility type of problem here. Yeah, so this is like a KSP type problem because we're looking for the molar solubility. So if I flip the page, so I got more places to write with. We'll take our overall here, which is our silver chloride was left, plus our couple of ammonia, making this guy, and chloride, and our K value that we got from combining 2.4 times 10 to the minus 3. So in this case, the only thing that was given to us was actually the molarity of the NH3, right? Which was 1, I hope. We don't have any of these guys given to us. So since this is really more like a solubility problem, because we're looking for the solubility of it, we're going to treat it the same way, which means this actually will be plus 2s, yes, even though we normally don't have stuff on that side. This will be, I'm sorry, minus 2s. Minus 2s. This would be plus s, and this would be plus s in this case. So a little bit different because we do have that ammonia on the left-hand side. And again, it should be minus because obviously it's on the left-hand side and decreasing. That means when we reach equilibrium here, we will have 1 minus 2s, s, and s. This will go into our K expression of our products over our reactants, and we do need to square the ammonia because of the coefficient. So I'm going to put that in. That's going to give us 2.4 times 10 to the minus 3 is equal to s squared divided by 1.0 minus 2s squared. I could solve that by doing what? Yeah, big old square root, right? Seems like a good move. Since we're getting to the end, I think it's a really good move. We're going to square root it there, and that's going to be 4.90 times 10 to the minus 2 equals s over 1 minus 2s in this case. We're going to multiply this to the other side, and that will give us 4.90 times 10 to the minus 2 minus 9.8 times 10 to the minus 2s is equal to s. Yes, I believe. We're then going to add this back to the other side, and that will get us 4.90 times 10 to the minus 2 is equal to, again, that s by itself is a 1, right? 1 plus 9.8 to the minus 2. Going to basically give us 1.098 s. dividing it to that side will give us 4.9 to the minus 2 divided by the answer, a molar solubility of like 4.5 times 10 to the minus 2. And that would be the molar solubility of silver chloride in ammonia. If we multiply that by the molar mass of silver chloride, that is roughly about 6.39 or 6.4 grams per liter. That's a lot of silver chloride, yes, that you could actually get to dissolve, not really dissolve, but make this complex ion. For comparison purposes, we did this calculation in water earlier. And in water, silver chloride solubility is 1.3 times 10 to the minus 5, which means if you take 1.3 to the minus 5 times it by the molar mass of silver chloride, you could get a whopping 1.86 times 10 to the minus 3 grams per liter, which is 0.002 grams. Which one is it more soluble in? Definitely the second one, which you could get about 6 grams of it to actually make the complex ion in that case, right? So I wouldn't say soluble, but it can make the complex ion, which I guess is soluble since it is an aqueous guy. So this demonstrates the idea that KFs are extremely large values, which means when there's an opportunity for a complex ion to be formed, it wants to make the complex ion. It will actually rip it apart. That's actually how you get rid of silver chloride solid. You add some ammonia to it, it will go away. And it really didn't go away, but the silver ended up in the ammonia and makes this complex ion, and you can redissolve it and stuff like that. So the formation of a complex ion is definitely favored when it is